All right, 20.4, our first calculation for this chapter. Cell EMF. And we call cell EMF, it's cell potential. So you're going to see this word many different ways. And AP uses both. I wish they would just stick to one. Okay. Explain whether an electrochemical cell is thermodynamically favored based on standard cell potentials and the half reactions in that cell. So determine from the electrochemical cell if it's thermodynamically favored or not. Electrochemistry encompasses the study of redox reactions that occur within an electrochemical cell. So in electrochemical cells, ladies and gentlemen, it's those beakers. So as you saw in our picture up here, okay, these are the electrochemical cells. Okay, and I don't think we labeled it last time, we just called them cells. But these guys, electrochemical cells. Okay, that's the whole point of that redox. Okay, the reactions are either thermodynamically favored, and we want it to be favored because a voltaic cell is favored. Okay, we want that positive voltage, or it's either not thermodynamically favored, which means that voltage would be negative. And the value of it, it's called E little degree sign for standard state. Standard state's not disappearing. And sometimes you may see the word like little cell, like written as like a subscript. And we want positive. That's a good thing. And requiring an externally applied potential for the reaction to proceed. That's that wire. Okay, so we need that wire. The standard cell potential, okay, which standard cell potential, that's that E cell. So this guy right there. Can be calculated by identifying the oxidation and the reduction half reactions, and then we need a data table. We need a chart. Standard reduction potential values. So it's usually, you'll see a data table on the AP test, okay? And it'll kind of look like, I'm kind of sneaking this over here. It'll look just like this, okay? And I'm going to be working this example with you guys, okay? The flow of electrons from anode to cathode is always thermodynamically favored. It has to go that way. Oops. Has to go that way for it to be spontaneous. What's the driving force? You got to remember, ladies and gentlemen, the electrons, they're attracted to that cathode. So the electrons are attracted to the cathode. And what happens is the cathode has what's called, very important here, the cathode has a lower electrical potential energy. So what you're going to see is this symbol called E with the word red for reduction. And that value right there is very low for the cathode. It has a lower electrical potential energy than the cathode. What we do is we're going to take the difference. And in math, ladies and gentlemen, that's called subtraction. We're going to be taking the difference between the anode and the cathode. And the units that we're going to be using is our new unit called Mr. Big V, big volts. Okay. Now, we're talking also about energy because it says the potential energy, a lower electrical potential energy than the anode. So this E reduction is very low, and the anode actually has a higher value. That volt, if we're going to have to convert it to energy, what a volt equals is a J over big C. And what big C is, it's called coulombs. And I know you've heard that word before, okay? Coulomb's law. So 1 big J over a coulomb. And what a coulomb measures, it's electrical charge. So 1 electron charge, 1.60 times 10 to the negative 19 coulombs, okay? Never had to use this number before, but I'm just telling you what the coulomb is. But we will be doing this in the last section, big time, and 20.9. So get ready on how we're going to convert those volts into joules. Electromotive force is EMF. Okay, and I don't know if you've ever heard of EMF before, but if anyone has ever known anyone that's like an electrician that messes actually with electricity, they probably definitely have heard of EMF. We in chemistry prefer the word cell potential. And what cell potential is capital E with the word cell. It's EMF. They are the same thing. You can even call it cell voltage, cell potential, EMF. They all mean the same thing. And for this thermodynamically favored reaction, we want positive. It's got to be a big positive. The bigger the positive, the better. With standard potentials, kind of just like delta G, so like delta G, standard state, we need that 1 molarity, because I told you we're going to be messing with concentration now. We need that 1 atm. We need that 25 degrees Celsius for that to be standard cell potential. And we have this new abbreviation called E little degree sign cell. So remember I told you we're going to be subtracting two numbers. It's a simple calculation, but I'm going to show you where students screw it up, okay? We're going to take the cell and we're going to take, remember, I know I put them somewhere. Remember this thing right here? Said the standard reduction potential values, okay? It's a data table, and that's why they call it E-red. You're going to take the cathode and you're going to minus the anode. And I know you're thinking, well, okay, that's easy, just subtracting two numbers. Yes, but these values have to be in reduction form. So these values right here, they're in a reduction looking equation. You got to remember redox, ladies and gentlemen, someone's got to be oxidized, somebody's got to reduce. But look at this data table. Notice the electrons on the reactant side. This electrons on the reaction side. These values right here, they're in a reduction format. Both of them are in a reduction format. However, somebody was oxidized and somebody was reduced. So when you grab these numbers, ladies and gentlemen, because it's in this chart, I just put it in your OneNote right here. On the AP test, you used to get 3 charts. You used to get a periodic table, an equation sheet, and this guy, the standard reduction potential values. Every single one of these half equations, they're all in reduction format. And I've already transferred it to your guys' notebooks, okay? So notice where the electrons are. Reactants. All of them are on the reactant side. You don't see not one electron on the product side. So you take these values and you just subtract them. That's it. Feyerabend does it a different way, which I've done it that way, and students don't do so well that way, okay? They do it better this way. So if you watch a little bit of Feyerabend, just beware. He does it a different way. You still get the same answer, but he does it different, okay? Cathode minus anode. So we just take those values from the standard reduction potential values, okay? Remember I said it's a data table. Oops, go away. Okay, so they will usually provide you with some type of data table in the equation, and all of them will have the metal or somebody with the electrons on this side. Oops, we'll call it the ion. The ion with the electrons, and then you get the piece of metal or non-metal, okay? You need it to be in that format. And when you subtract it, we want positive, because positive voltage is what we call a good cell, a good battery, because what a voltaic cell is, it's a battery. Okay, that's why you always see on a battery, there's a positive end and there's a negative end. And that means it is definitely thermodynamically favored if that E cell is positive. When we have coefficients, ladies and gentlemen, they do not, okay, and we're so used to taking coefficients and either multiplying or squaring them. Don't, okay? So I'm going to do an example with you. So these stoichiometric coefficients, ladies and gentlemen, do not do anything with the coefficients with it in regards to this guy, okay? So don't mess with them. We just need it more for balancing equation purposes, okay? So I left space for me, but you're going to see some writing there, so you may want to get a piece of paper because I'm going to show you the calculation for this one. This was the equation that was in the video for 20.3, okay? But I gave you the answer, but I told you in the video I'm going to show you where 20.4, how to do the calculation. All right, so step number 1, let's pretend like we don't even see this answer. Okay, so remember in 20.3 we had, and let's get back to memory lane, we said the zinc was the anode and the copper was the cathode. Okay, and even if I didn't tell you that, ladies and gentlemen, you would know who is who by looking at the balance equation. Now look at this, zinc, perfect zinc, and now it's zinc plus 2. I know my zinc solid went to aqueous zinc, and what happened is he lost 2 electrons. Okay, so I know right there that's oxidation, and that means that zinc was the anode. Okay, my copper went from plus 2 to perfect copper. Okay, and where are my electrons? Well, if he was reduced, I need to have my electrons on the reactant side. So he was reduced because copper was the cathode. Now let me show you how to use the chart. We got to find these 2 half reactions. Now remember, ladies and gentlemen, you're not going to have this big mamma jamma chart anymore. AP is going to give you like a simpler version like this, okay? And you're welcome. But on here, we got to find it. So we're looking for the zinc right here. We're looking for him. And his standard, which means 25 degrees Celsius, 1 atm, 1 molarity, okay, all of that is for these values. That value right there is negative 0.76. So negative 0.76, and this is big V volts. But look at the equation, ladies and gentlemen. They wrote it this way. They wrote it in reduction form. So this value right here is the reduction form of it, okay? Which basically means this equation right here is opposite, okay? Don't do anything to this E value. This is where Fairbra and me, we do it differently, okay? You just take this value and just leave it alone. That's it, okay? But it's in reduction form, this value. I'm going to take the copper, and I need to find this equation where it's the plus 2 going to the copper solid. So I'm going to go to my chart, the copper plus 2, and I'm looking for this one. If you notice the equation right below it, oops, this one goes to the ion, an ion to a different ion. I need the plus 2 to go to the solid, and that's a positive 0.34. So this E reduction is 34, okay? Now, simple equation. The E cell, you put the E of the cathode minus E of the anode, okay? That's literally all you got to write. Our cathode, remember cathode was copper, and the copper was 0.34 volts. And our zinc was the anode, minus 0.76, okay? And this value right here is negative. So this value minus this negative anode. Well, obviously that's going to become positive. So when you plug that into the calculator, ladies and gentlemen, our E cell is positive 1.0 volts, and that is a good cell. So is it thermodynamically favored? Absolutely, since E cell is positive. So when we calculate delta G, we know our delta G will be negative, okay? So when we actually get to that calculation. You're going to see many different people do this calculation different ways, and it's going to confuse you. That's why I'm not putting Farabrah's video on the Teams, ladies and gentlemen, because he does it, like I said, differently. Okay, it's not wrong. It's just every professor does it differently. Every teacher does it their own way, and I've always learned it this way from college. I've always done it this way. It's this part right here. Just because, ladies and gentlemen, that this is in, let's do it in a different color. This is in oxidation form. So what happens is in oxidation form, what happens to this value? In oxidation form, it's a flip of the sign. Okay? If you flip the equation and put it in here, you're going to get a negative value for E cell, and we can't have negative because the whole point of a voltaic cell is it has to be positive. Okay, so this is where Farabrah does it differently. If it makes sense to you to do it this way, absolutely go for it. Okay, but just get the right answer. Okay, so Farabrah's method. He takes that zinc equation because he sees it, and I wasn't going to show it to you, but I know some of you guys, you understand his way too. And this value right here on the reduction potential chart, it has it as negative because it's in reduction form. So because this is oxidation, you take that value and you flip the sign. Okay? So whoever was oxidized, you take the reduction potential value and you flip the sign. Okay, and I know you're thinking, well, how is the answer going to get positive if I'm going to flip the sign? Okay, hold on. Now we still have the reduction. We're not going to do anything to copper because he's already in reduced form. So our copper and this copper, and actually I'm going to take that word red off, and actually this is now going to say oxidation instead. So because we flipped it, it's not in reduction form no more. It's in oxidation form. And this one's still going to be 0.34 volts. Okay? Now here's his equation. Because we flipped the sign, it's still the cathode and it's still the anode. But because the anode is where oxidation occurs and you flipped it, you add it instead. Okay? And if you add that, ladies and gentlemen, you get the cathode was 0.34 added to that 76. And you still get the same answer. I prefer the way I've always done it. Makes sense to me. But if you understand Farabrah's way, okay, I don't mind putting this video up there. I just don't want you to get confused. Because when I lecture, ladies and gentlemen, I'm going to be using my way. Okay? And not because it's my way, it's just the way that it's always been done. Okay? So either way, but it is a difference in equation. One way subtracts them, where they just use the values on the chart. The other one flips the sign. Okay? But it's adding. Okay? So when you use this one, no flipping any signs. Okay? Regardless of oxidation. Okay? But this one actually flips the sign where you're going to go positive. Okay? I want to show you an example, the one from AP Daily. Okay? It's only because in the book we're definitely going to be doing those examples. So I wanted this one because they don't tell you who's the anode or the cathode. You have to figure it out from the picture. So we have one cell that's zinc ions, the zinc solid, and that's its cell potential value. So remember right here, these are called cell standard reduction. Actually, not the word cell, but just standard reduction potential values. Okay, and notice these half equations, they're in reduction form. Both of the electrons are on the reactant side. I got aluminum and zinc, going to do an equation. And according to this picture, you should be able to figure out who is oxidized and reduced. And how would you do that? Is look at the electrons. Look at what the electrons are doing. I don't want you to think, ladies and gentlemen, because I drew a picture that I put the anode on the left side and the cathode on the right side, because that's always how it's going to be. That's just the way I do it, because I do it alphabetical. So if you notice, these electrons are traveling over on this side, and that must mean that they are attracted to this electrode. And that should tell you that this electrode must be a positive electrode. And we call that the cathode, which means this is where reduction occurs. And this aluminum right here, because the electrons are leaving it, negative, because remember, same charges repel each other, this is the anode. And this is where oxidation occurs. So this is where they don't have to tell you, that you have to figure it out from a picture. Okay? So write the balance equation for the following, and then we're going to calculate E cell. Now there's like not a lot of room up here, so I'm going to be doing my work down here. See these electrons right here? I need them to cancel out, and they're not going to cancel that way, because what happens is with aluminum right here, I'm going to flip only the equation, because I need this to be an oxidation form. So I'm going to flip this, and for purposes of your work, ladies and gentlemen, you don't have to put states of matters in the work. You only have to put states of matters in the overall equation. So I'm going to flip this. Okay, and that's what my equation needs to be. Right here, I'm doing part A. And my zinc plus 2, and my 2 electrons, and then zinc solid. Okay, well, if they can't cancel out, you got to find a factor to make them cancel. And what that factor is going to be 6. So I'm going to have to multiply this whole equation by 2, and I multiply this equation all by 3. So then I just show this work right underneath it, give it like a little space, and 2 aluminum, 2 Al plus 3, and now I got 6 electrons. And then I take my zinc, and, oops, not a 6, and 3 zinc plus 2, and 6 electrons. And make sure you put the little negative on electrons, they have a charge, and 3 zinc. Okay? Now, my 6 electrons, electrical neutrality right there, okay, are balancing out. And now I write my balance equation. And this is where your states of matters come in. Basic chemistry, ladies and gentlemen, ions are always aqueous. My aluminum is a piece of metal, and my ions are always aqueous, and my zinc is a piece of metal. Basic chemistry, ladies and gentlemen, you better make sure you check your charges. Okay, not just check that the equation's balanced. Okay, I see 2 aluminums and 3 zincs. But right here, 3 times plus 2, that's a plus 6. No charge on aluminum, 0. 2 times plus 3, plus 6. No charge on zinc. They have to equal each other. Okay, that's the point of electrical neutrality. Okay, so that is what you would be boxing your equation for AP. Now part B, you got to remember, when you multiply the coefficients on your equation, okay, you do not multiply any factors to the E reduction potential values. You just leave those values alone, ladies and gentlemen. Just bring them down. That's it. Don't. It was even in my notes. And I'll show you where. Right here. Changing the coefficients does not change the value of those E reduction numbers. Okay? Leave them alone. Leave them alone. So, my aluminum right here, if I go back to my chart right here, my aluminum, even though this is an oxidation form, and this is the one that was reduced, I'm going to take my E cell, and I'm going to label it exactly like this, my E reduction, And I'm going to put the word cathode because I'm just going to take those values and just subtract them. I don't want to flip anything. I only flipped my equation. And my E, and I put the word reduction, and then my anode. Okay, so my cathode was zinc. So I'm going to take that value for zinc up there, which was negative 0.76 volts, minus, and I'm going to take the anode, which is aluminum. I'm going to take the value, not flip or anything, negative 1.66. Okay, and when I plug that in, ladies and gentlemen, sig figs and all, my E cell will be a positive 90 volts. And that is thermodynamically favored. Okay, we need that thermodynamically favored value because that's the point of a voltaic cell. Okay, so hopefully that makes sense to you. You want to flip the sign, that's fine, but then you're adding instead of subtracting. Okay, not that complex. How were these values measured over time? Well, they used what's called the hydrogen atom. So what happens is with standard reduction, we can't actually measure them directly. There's just no way. So the scientist involved with this, he created a standard, and the standard is called the hydrogen electrode. So all these half reactions are written in reduction form, not in oxidation. Okay, so don't flip any signs. Okay, as long as you want to subtract, don't flip any signs. So the standard hydrogen electrode. And the problem is, well, hydrogen's a gas. How do you even do an electrode for a gas? Well, the standard hydrogen electrode, the potential that they assigned it to, they assigned it to 0. So when they first were doing experiments, they took ions of hydrogen in an aqueous 1 molarity solution, gave it some electrons, and then they made diatomic hydrogen gas. Well, that value is 0. So if they knew that the cell potential for the hydrogen, so right here, here's hydrogen, they knew that this cell potential, this E reduction value, has a voltage of 0. And if they were trying to figure out the other electrode that was in here, well, they knew a number minus 0 has to be that number. That's how they figured out all these values. They kept doing reactions against hydrogen because they created hydrogen as the standard. So what do you do if it's a gas? It's like a little glass tube. And the wire, this piece of metal that's in here, I know it's really hard to see, it's platinum. So what they do is they take this wire and this piece of platinum sitting right there in this glass tube. This is where the hydrogen gas, this is the gas that's coming into it. And the gas is coming in, and the gas is turning in to aqueous solution, some aqueous ions in here. And why platinum? Well, remember back in the day we did a thing called the activity series. Platinum is very unreactive. I mean, they could have used gold or silver. If they wanted to, they could have. It's very, very unreactive. We didn't want the platinum to mess up the experiment. We wanted the hydrogen to be the star of the show. So we call it the SHE, the standard hydrogen electrode. So if the hydrogen was 0, trying to test zinc to figure out his cell potential, then that's how we figured it out. The same number minus 0 gave me the value that we needed. Okay, so that's how these potential numbers came about. You won't be asked about the history of it. I'm just showing you how these values came. The name of the game is to get that positive value. We want that thermodynamically favored reaction. And if it actually goes negative on you, which it shouldn't, okay, then it would be spontaneous in the oxidation route. Okay, but we like to look at it as the reduction value. The more positive it is, okay, the greater the driving force for reduction, okay, to push those electrons through that circuit. So when we look at this chart, okay, and we are not looking at agents in here. This is one of the reference pages that we used to get with AP Test. That's why I said I got to update some notes here. With this, sorry, Mama Rojas is texting me right now. All right. So on this chart, ladies and gentlemen, the reason why I liked this reference page It was the activity series backwards. Okay, so down here you have the most reactive metals. Up here to the least. I mean, look, you got gold up here, you got silver right here, you got some mercury, and it doesn't obviously have all the elements on here, but you don't see like lithium and sodium or anything. So these are the least reactive metals. And you do see some nonmetals in here. You see fluorine, you see chlorine. So the least reactive, I'm just looking at the metals right here. Okay, but in the notes, that's why it makes me sad, because it was the activity series backwards. The more positive the value is, the more likely that substance will be reduced. So when you're looking at here, ladies and gentlemen, see these positive values? The more positive it is, the more likely it will be the cathode, because it would prefer to be reduced. Okay, so when you're looking at this chart, even if they didn't tell you, even if they didn't give you this picture, the one that's more positive is the one that's going to be the cathode. And I know you're looking at two negative numbers, but who is the least? Sorry, my dog. Isn't that bark cute? The one that is the least negative right here. Sorry, I'm not even concentrating right now. The one that is, oh my God, this is where editing is very important. Right here, this is more negative, and this one is less negative. So the zinc being the less negative is the one that's going to be the cathode. So even if you don't have this cute little picture here, looking for the one that's most positive, ding, 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 is the cathode. Okay, so that's how you also do it too. More positive, the more likely it's to be reduced. The more negative it is, the more likely it will be oxidized. Okay, so down here, more likely to be cathode, and down here, more likely to be oxidized, which means the anode. Now I want to tie something in here, ladies and gentlemen. Look at who we're talking about in here. Lithium, group 1, group 1, group 1, group 1, group 2, group 2. Oops, that's a 2. Group 2, group 1. What do we know about valence electrons? The name of the game is to get to 8. You got 1 valence, 1 valence, 2 valence, 1 valence, 3 valence. They're never going to get to 8. So wouldn't they prefer to lose? And that's why they're more likely to be oxidized. You got non-metal, non-metal, non-metal. They want to gain, okay? I know they don't have feelings or needs, but they're going to gain electrons. And that's the point of this, ladies and gentlemen. It should be tying this all in back from chapter 4 in basic chemistry. If it's reduced, they're going to gain electrons. And if they're going to lose, they're going to be oxidized, okay? So that's why this chart, I miss it to death because it really helps tie things in. No, we're not memorizing numbers, okay? Heck no, we're not memorizing numbers. But right here, as you see in the middle, there's the standard hydrogen electrode, okay? So that is the standard that started it all. The more positive, more likely reduced. The more negative, oxidized, okay? So I even put that in here right there to help you guys. We are not doing